Let's get that going and let's get started. All right, so chapter 9. Well, quickly, let's talk for just a second about chapter 8. What did we just finish up? I know it's been a bit since we had like our midterms and our Christmas break. What's the last thing we covered? What was the last chapter all about? What was our last postulate we were given?
Parallel lines.
Parallel lines. So our last postulate was about parallel lines. Our last chapter was all about parallel lines.
Yeah.
Quickly tell me, high-level language, what was our last postulate?
On high-level language, parallel lines is two lines that don't.
So parallel lines is two lines that never intersect, but what was our last postulate?
The angle sum of straight angle. The angle sum of triangle is straight angle.
That was the last theorem we proved, I think, but not our last postulate. The last postulate was if you have a line and a point not on the line, there is only one line I can draw through the given point such that the two lines are parallel. We proved that there is at least one. We showed how to construct that without the postulate, and the postulate is that there's only one. And that's where we made our divergence from potentially being hyperbolic geometry.
All right.
So we have a lot to say about parallel lines. So now this next section is about similar shapes, in particular similar triangles. Again, using high-level language, what does it mean for two shapes to be similar?
For them to be congruent.
No, congruent means congruent. What does it mean for them to be similar? So a triangle like this might be similar to a triangle like this.
They have the same
Angle sum.
The angle sum of every triangle is 180 degrees. These two triangles are similar, kind of. Obviously my drawing's bad.
because the angles are the same.
These two triangles are not similar.
Because they're not the same type. Those are both equilateral, and that one's a right triangle.
Right, so with the triangles, we say the angles, as long as the angles are all the same, then the two shapes are similar. That happens to be true. But notice that that wouldn't be true for four-sided figures. For example, this is not similar to this.
So
These are not similar shapes. So we say that two shapes are similar. We'll give the exact
That's
definition.
fine.
But it needs to be like a scaled down or scaled up version of the shape.
Right.
That's what we mean for shapes to be similar.
Right.
So this section is all about similar shapes, in particular similar triangles. Use similar triangles a ton in mathematics.
Okay.
Very useful to have similar triangles show up some way. A lot of trig is dedicated to that kind of study. Okay, so high level, that's what this chapter is going to be all about. Now, I'm going to do a quick lemma that the author, he seems to use this information, but I couldn't see where he ever actually used it. So our first lemma that we're going to prove here today is that opposite sides of a parallelogram are congruent. What's a parallelogram?
Is it square or rectangle?
It's a four-sided figure, yep. Where both sides are parallel to each other. So here's a potential parallelogram.
Right.
So quickly, I want to prove that its opposite sides are congruent. I want to prove that this side is congruent to this side and this side is congruent to this side. That's what I'm going to do really quick. Right? Meaning they have the same length. That's what it means for two segments to be congruent. Remember, a side of the figure is just a segment. Okay, so first thing I'm going to do here is I'm going to add a diagonal.
You're going to prove those triangles are.
I'm going to prove that these two triangles are congruent.
Right.
And so that side will be congruent to that side, and that side will be congruent to that side. That's the whole crux of the proof.
Super easy.
So first off, remember that we know that this side is parallel to this side. Now, since this side's parallel to this side, this diagonal right here is a transversal. And so this angle and this angle are opposite interior angles.
Right.
So they're congruent. Similarly, I know that this side is congruent to this side.
Parallel. Yeah.
Or thank you, parallel to this side. And so you can view this as a transversal through these two parallel lines. And so this angle is congruent to its opposite interior angle, that angle.
Now you have an angle side angle.
Now we have an angle side angle, because notice that this side is congruent to this side.
Right.
So you get that this triangle is congruent to this triangle. So I give you this side is congruent to this side, and this side is congruent to this side. You get on that proof?
Yep.
Okay, quick lemma, we're going to be using that fact a bit throughout the section. Okay, so now our first theorem that we're going to prove today is if L, L prime, and L double prime are parallel lines, and M is a transversal intersecting the lines at points A, B, and C. So let's see, we start with 3 parallel lines. So we have a parallel line L, we have a parallel line L prime, and we have a parallel line
L double prime.
L double prime. Not L squared. L double prime.
Going to the bottom now.
Yeah, they're been accumulating a bunch of bad ones. And if we draw a transversal on this M, so here's M, and it intersects at the points A, B, and C. And it does so in such a way that AB is congruent to AC, or to BC. So those two segments are congruent. And then if you pick some other transversal, doesn't matter which one, I may call it M prime. Here's another one. Hopefully it's obvious that those are slanting at different angles.
Yeah.
We are trying to prove that this segment is also congruent to this segment. So I'll say that this intersects at the points A prime, B prime, C prime. A prime, B prime, C prime. Our job is to prove that this segment A prime, B prime is congruent to the segment B prime, C prime. So what's given in this is I know that AB is congruent to BC. I'm trying to show that A prime, B prime is congruent to B prime, C prime. Understand the proof?
Yes.
All right. Let's figure out how to do this proof. Okay, first thing I'm going to do is I'm going to construct 2 parallel lines, 2 lines parallel to M. One coming from the point A, one coming from the point B.
Okay.
So first I'm going to create this, hopefully.
So you're saying off of M to parallel to M prime.
So we'll call it M double prime so we remember it's parallel to M prime. Maybe I shouldn't call this one M. Let's call this K, and then I'll call this K prime. That way, based off the letters, we keep track of what's parallel to what.
Right.
And then I'm going to do another one here, which is
K double prime.
K double prime. And just remind ourselves of what we know. We know that AB is congruent to BC. Okay. So here's our picture so far. All right. What is our strategy going to be? My strategy is going to be to prove that this triangle is congruent to this triangle.
Right.
So this side's congruent to this side.
And then you're gonna.
And then I use our previous lemma, which says opposite sides of a parallelogram are parallel. So this is congruent to that, which is congruent to that, which is congruent to that. And then you get your transitivity that this is congruent to this.
Right.
That's big picture how we're going to go after this. You with me?
Yeah.
So the crux of the proof relies upon showing that these 2 triangles are congruent triangles. So wherever this line intersects L prime, we'll call that the point D. And wherever this line intersects K double prime, we'll call the point E. Okay. So I want to say this triangle is congruent to this triangle.
Right. We know that angle
You know that their sides are.
ABD is congruent to angle BCE
We know ABD is congruent to BCE. How do we know that?
because they're. We do not. We 100% know that they're.
We know that.
I can't remember what it's called, but it's basically like where they're in the same.
Look at these 2 lines are parallel.
Oh.
These 2 lines are parallel. Here's your transversal, M's your transversal. This angle and this angle, we call those corresponding angles. We have everyone. So, this angle is congruent to this angle since they are corresponding angles. Similarly, look at the top angles of each of these.
They're.
Here's our 2 parallel lines this time.
You're right. Yeah, they're corresponding. Absolutely.
So viewing this as our parallel lines, and this is our transversal, now this angle is a corresponding angle to that angle.
Now you have angle side angle.
So that angle is congruent to that angle since they are corresponding angles.
Now
When you view your 2 parallel lines as K prime and K double prime. You see it? Okay, now we have by angle side angle,
2 triangles.
those 2 triangles are congruent. So that gives me that this side is congruent to this side.
And because.
Now by construction, AD, B prime, A prime is a parallelogram.
Right.
So I know that AD is congruent to A prime, B prime, And by construction, the BEC prime B prime is a parallelogram, so I know that that's congruent to that. Then by the transitive property of congruence, I know A prime B prime is congruent to B prime C prime. See it?
Yeah.
Think you got it?
Yeah.
So by default, I'm just going to walk you through the logic of any of these. If you want to see the full proof written out, say that. But just for the sake of time, I'm going to try and push forward. So we can always write it out if you want to see it, but if you think you got it, you think you got it. Think you're good? All right. So that was theorem 9.1. Then we have two quick corollaries. Okay, so looking at that picture, imagine now for a second that I redid this whole proof, but I matched A up with A prime.
What do you mean?
So imagine I could pick up this line K, and I dragged it over until A and A prime coincided.
Okay.
So then it would have made a triangle like this.
Right.
Where now, here's the points A and A prime. This we're just now going to call B, this we're going to call C. So we got a triangle, but now this parallel line that went through the middle, that's going through the middle. So that's going through the middle like that. With me?
Yeah.
That parallel line goes through BC, that parallel line only goes through the point A. If I know inside this triangle ABC, so here's exactly what the corollary is. Call that the point D. If I know that D is the midpoint of AB, or in other words, this segment is congruent to this segment,
Right.
and I know that this line coming from the point D over is parallel to BC, so I know this line is parallel to this line,
Right.
then wherever it intersects over here at a point E, wherever it intersects over there, has to bisect this side. That has to be congruent to that. So if I
Way
was...
easier.
Huh?
It's way easier then.
It's way easier than
Wait, what is he
It's
trying
way
to
easier
prove?
that way than the other way. That's what I'm saying.
This is a consequence of this. Look at what this said. This said that when you have this line and this line, as long as you have these parallel lines going through it, if you bisect over here, you also bisect it over here. That's what we proved. Now we're saying take a triangle, draw a parallel line, a line parallel to the bottom that bisects this side. It's going to also bisect this side. Notice that this picture and this picture are the exact same picture if I would pick up this K and I'd move it over until it lied directly on K prime.
Right.
Then the proof is identical. So this is just a special case of what we had over here. You see that?
Yeah.
Yeah.
So we know if you've got a triangle, let's make sure we understand exactly how we can use this. I've got a triangle. I go to one of its sides, I pick the midpoint, D.
Right.
From D, I draw out a line parallel to the bottom line. So I draw this line, so it's parallel to this line.
Right.
Then wherever it intersects over here is going to bisect that side as well.
Right.
B and midpoint, bisect it, yes.
It doesn't say the DB is the same length as
So that's a word that I know you guys have misused on your test a couple times. Bisect means to intersect it right at the middle.
right.
That's
Divide
what
into
bisect
two.
means. Divide it into two. So it bisects it. Okay, second corollary that we get for free from this. The second corollary, not that we get for free, a little bit of work, but is now I've got a triangle, ABC, not necessarily equilateral, just kind of find it. ABC, I've got that triangle. Pick the midpoint over here, call that D. So that's the midpoint of that segment. Pick the midpoint over here. So that's congruent to that, we'll call it E. And draw the line through the midpoints. The second part of the corollary is the line that we drew is in fact parallel to the given line. Now we need to prove that. What we did up here is we said start at D, draw a line parallel, and it happens to bisect over here. Now we're saying pick the segment that happens to bisect these, and we need to prove that it's parallel to the base. So that's what we're trying to do now. A little bit different than what we were doing before. You understand the difference in the proofs?
Yes.
Okay, so I'm trying to show that this is parallel to this. How am I going to do that? I'm going to go from point D, and I'm going to construct the line that is parallel to this line.
Good.
So I'm going to come to D, I'm going to draw this line, and this intersects over here at F, and I construct it so that this is parallel to this. I need to argue that F and E are really the same point.
Right.
And so this line is in fact the same line. You with me? Now by this corollary, I know that wherever F lands, it has to bisect AC.
Guess what? E bisects.
Guess what? E bisects AC.
Yeah.
There's only one point that bisects it. F does it, E does it. Therefore, F and E are the same point.
Right.
Therefore, F equals E, which is basically what we were after. They're the same point. That's the end of that corollary. Good there? Okay. So those were the two corollaries he had. If you're following along, that was just corollary 912 that we just did. Exercise group, now construction. Okay. This is kind of a neat construction. So, kind of shifting gears a little bit now. Think about this problem. Here you are, you're one of the ancient Greeks. You know, you're building some massive temple. You know that you're going to have to put up 6 pillars, but you need them to be evenly spaced. So here's our problem. Our problem is that we've got this distance along, you know, some temple wall or whatever. And I need to put up exactly 6 pillars, but I want them to be evenly spaced. Or in other words, I need to break this up into 5 even spaces. How do we do that?
Back in their day.
Yeah, well, even now, how might we do that? You might think we measure this whole distance, we divide it into fifths, and then we calculate 1/5 of that distance going forward. One problem you run into right away is that measuring this can be kind of an infinite process. It might not come out nicely. We want to get as perfect as we can get. Because if we go and we measure this, you might say, okay, let's start by measuring it with the marker lids. How many markers was it? It was 1, 2, and then a little bit, so 2. And how many lids, and maybe we count how many lids it used, and that's not going to quite be accurate enough. And we have to keep using smaller and smaller instruments. It might not come out perfectly. In fact, it's very likely it doesn't come out perfectly. And then you got to do the math of dividing it up. So how did the Greeks do this? And remember that the Greeks didn't even have a notion of measurement in their geometry. They didn't even measure the lengths of things. And they figured out how to do this problem. It's pretty simple for them.
Make a circle.
Make a circle. I don't know what making a circle is going to do. Make a circle around the whole thing?
No, you just say you use the 2 sides as a circle so that you know the length of it. Because the circle.
So once you know the length, even if we get the length, now we got to divide that length up into fifths.
And it's going to be a point something.
And then you got to somehow get your compass exactly at 1/5 of that length. And now you're fidgeting around. It's much easier if we can just lock in our compass to one value and then just work it out from there. So here's how they did it. They said, just pick some line, doesn't matter. Now, we know how to set our compass to a set value and move our compass over and over again without changing how wide open it is. We can't open it to exactly 1/5 of that. There's no way for us to do that. But we can open it to some value and then lock it in at that value and keep using that value over and over again. To measure off distances of some length. Right? That's our whole concept of measuring. Measure off this many of the distance and then...
Right.
Alright, so pick our length, doesn't matter what our length is. And we're going to count them off. How many did we want? We wanted to split that up into 5 segments, right? So we're going to count off 5 of those. So we'll pretend that the length I had was yay big. Pretend this is perfect, but obviously it's not. So we count off 5 of those. 1, 2, 3, 4, 5. Now what do we do?
That's 6 segments.
1, 2, 3, 4, 5.
Never mind.
So we're going to be putting up 6 pillars, 5 segments, right? Okay. Now, we connect this point and this point with a line segment.
Wait, it can be any line going whatever way.
Any line going whatever way. Our job is, let me re-scratch this in green. The green one, we have to divide up perfectly into 5 pieces. So we got to divide the green one up perfectly into 5 pieces.
Yeah,
That's our job. Okay. So here we go like this. Now, our first construction from last chapter was I showed you how to construct a line parallel to a given line through a point. Our postulate was, and there's only one line, but before the postulate, the first proof we did is I showed you how, given a line and a point not on the line, how to construct a line through the point parallel to the given line. So we've already gone over that construction. You want to re-see that construction, go to last week's lecture. But we know how to construct parallel lines, and we know how to do it perfectly. And so, what do? We now come to this point, and we construct a line perfectly parallel to this line. which would be, obviously I'm not going to do it very perfect, but like that. And we do the same thing here. And we do the same thing here. And we do the same thing here. Now, using our theorem over here, by construction, I already knew that this was the same length as 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 this.
Right.
How do you know that?
Because
That was by construction. I stuck my compass at, I picked some random line, I stuck my compass at some random length, doesn't matter, but I kept it as that length, as I kept marking off distances.
some random like you could have done one that was way longer than that.
In other words, I stick my compass right there, I draw off a circle which gives me 2 points. I move it over to this, draw the same circle. Move it over to this, draw the same circle.
Oh.
Mark it off lengths as we go. So I only ever have to set one value. What's the length of the value? I have no clue how long these are. Didn't have to do any measuring. I just locked in my compass at some length. What length? No clue. Some length. All that matters is that's the same length as that, is the same as that, is the same as that, is the same as that. Now using this theorem over here, since this line and this line and this line are all parallel, this is congruent to that. Looking at these 3 parallel lines. Now look at these 3 parallel lines, that means this is congruent to that. And this is congruent to that. And this is congruent to that. Using our triangle one that we just did for the last case. And so, we just broke that up into 5 even pieces. And so, here's where you place your 6 pillars if you want it perfectly split up. So there we go. Perfectly dividing up a distance into 5 units. No measurement involved.
If you don't know what the length on your compass is, what if it gets clear down there? Like,
We could have. So, in this case, my point happened to line up nicely with this.
Right.
yeah.
If that was an accident. If I would have picked a longer distance, so my first parallel, if it would have ended here, my first parallel line would have gone like this. My second parallel line would have gone something like, I don't know where my next point would have been, but somewhere like right here. My third parallel line would have been like this, and it still would have worked out fine. Doesn't change it. So it happened to come out kind of pretty, but that was an accident. Yeah, it's cool construction. No measurement involved, perfectly divided that segment up into 5 pieces.
And they build structures crazy.
Now you can see why architects have to know geometry. There's a lot of really clever things you can do that even modern people now today with accurate tools of measurement might end up doing worse. Because they might go through the pains of trying to get a perfect measurement on that and then dividing it up into 5 and saying, yeah, kind of close enough, kind of close enough. You can perfectly line it out, pull your strings, have them come up exactly where they come up, you're good. So, yeah, ancient architects had to know a lot of geometry to lay these things out and make it look nice. That's that. So that's a neat little construction. So if you're following the book, that was construction 9.1. Now I think we put a pin in it and we talk about ratios for a second. Now, unfortunately, here's where you can get a little jaded because we now need to build off of the algebra review you did back in chapter 2. You remember that algebra review?
Yes.
Vaguely. Now, fortunately, just through random conversations off the camera, we happened to have talked about arithmetic a bit last time. And so we talked about how when you're doing arithmetic, you have plus and you have times as your undefined operations. And our 2 undefined numbers were 0 and 1. You remember our conversation about that?
Yeah.
And we talked a little bit how we could define other numbers in terms of 0 and 1 and using these operations. The important thing that we're going to talk about here for a second is defining 2 other operations, subtraction and division. So first I'm going to give you the definition of subtraction. Ready? So what do I mean by x is equal to y minus z? So defining subtraction. I need to define it in terms of addition.
It's the opposite of addition.
This means, by definition, here's what we're going to define it to be. This means that y, usually we do it the other way around, sorry. I should say x minus y equals z. So what do I mean when I say x minus y is equal to z? By definition, that means x is equal to y plus z. That's its exact definition. Using that definition, if I ask you to prove that 7 minus 3 is equal to 4, the way that you would go about proving that is you would prove that 7 is equal to 3 plus 4. You would prove that this is the case, therefore this is the case. By definition, this means this. By definition, this means this. It's its definition. It's kind of weird to wrap our head around that at first. So that's exactly how we define subtraction. How do we define division? Division, by definition, x divided by y is equal to z. By definition, what does that mean? It means that x is equal to y times z, where y is not equal to 0. There's our definition of division. What does it mean to say that x divided by y is equal to z? It means x is equal to y times z. Precise definition.
Yes.
Concrete example.
Yeah.
What do I mean when I say, if I were to say, prove to me that 15 divided by 3 is equal to 5, how would you prove that? You would prove that 15 is equal to 3 times 5. You're used to doing the operation in your head that uses this definition all the time. Going from here to here, you multiply both sides by y. And going from here to here, you divide both sides by y. Anytime you're doing that operation, you're really using this definition back and forth. You can go from this to this, and you can go from this to this, perfectly valid. That's its definition. There's some concrete examples. Okay, so why are we introducing this division? Because we're going to introduce the notion of a ratio. What is a ratio? A ratio is two numbers, x over y, x divided by y, where y is not equal to 0. Right? It's just dividing one number by another number. We call that a ratio. Now we're going to talk about numbers being proportional to each other. So you've probably read somewhere along the way that A and B are proportional to C and D. What does that mean? When I say A and B are proportional to C and D, that means A over C is equal to B over D. Concrete example. 1 and 2 are proportional to 2, well, let's say it like this, to 3 and 6. These two numbers are proportional to those two numbers, right?
Right.
The right one's double the left. The right one's double the left.
Yeah.
What does that mean mathematically? That means 1 over 3 is equal to 2 over 6. Our numerators over our denominators are equal.
Right.
And you can state out multiple proportionalities all in one go. I could have said x, y, z, and w are proportional to x prime, y prime, z prime, and w prime. What does that mean? That means x over x prime is equal to y over y prime is equal to z over z prime is equal to w over w prime.
So it's like a ratio, right?
Yes, that's exactly what we're talking about, ratios. So this is a ratio. This is stating an equivalence between a bunch of ratios. That's what proportionality states, that these ratios are equivalent.
So, x over x prime wouldn't be y over z prime.
Correct.
It'd only be that, right? Or y over x prime could equal x over y prime, right? That
So-
would work too, right?
You have to be careful when you're going to state multiple of them like this. So you can't just go flopping like that when you're stating multiple. But up here, it would have been the case when you're just stating 2, it would have also been the case that A over B is equal to C over D.
A over d is the same as b over c, right?
It would be. Yeah.
No. You can swap these two, and you can swap these two. You can't do the A and the D, you can't do the B and the C. Let's look at it with concrete numbers. You're saying A over D, that would be 1/6, is equal to B over C, 2/3. No.
Yeah, but you said they are equal.
No.
Wait, A is 1?
Yeah, A is 1, B is 2, C is 3, D is 6. Picking some numbers to plug in there. So you can say A over C is equal to B over D. That's 1/3 is equal to 2/6. I could have also switched these two if I wanted. Well, more commonly switching these two. I could have also thought about it as A over B is equal to C over D. So in that case, what would we have been saying? A over B is 1/2 is equal to C over D is 3/6.
Right.
1/6 is equal to 2/3.
1/6 is very different from 2/3. If I give you 2/3 of pizza, I'm giving you,
No.
yeah,
Both
that's almost the entire pizza.
If you want 6,
That's right.
Once.
1/3 is the same as 2/6.
Yeah, the numbers are so nice that you'll accidentally cancel things out that you can't do in your head.
Yeah, 2/3 is the same as 4/6. Not 1/6.
Okay.
1/3 is the same as 2/6.
Yes, 1/3 is 2/6. All right, so that's what we mean by proportionality. Now, notice here, the fact that I put these ones on the numerator and these ones on the denominator is arbitrary. I could have just as easily put all the primes on top and all the letters on the bottom. And it's still true. That would just be flipping the reciprocal of all your fractions. If 1/2 is equal to 3/6, then 2 over 1 is equal to 6 over 3.
Yeah, but look.
That's always in general true. If two fractions are equal to each other, flip their reciprocals are also equal to each other.
Yeah, equal to each other. They're not equal to what you had before.
Not equal to what you had before, that's why I'm saying, if we can flip the reciprocal on everything, then it'd be true. Not just on one thing. I can't just say, put the x prime up here and the x down there. Now that's a lie. But if I would have moved all my primes to the top, and kept all the other ones on the denominator, then it'd still be true. So when you're reading out some list, it's going to give you some list of these numbers in a list are proportional to these numbers, and then we'll say respectively, meaning preserving order. You can either think about here's your numerators and here's your denominators, or here's your denominators and here's your numerators. Doesn't matter. But you got to stick with one way or the other.
Right.
Okay, that's all we're stressing there. Okay,
Why are we going over ratios?
because ratios have a lot to do with similarity. That's what we mean by somehow the scale, yeah, you just rescaled it. If I'm going to say that this is similar to this is a rescaled version of this, what we mean is that all their sides are still proportional to each other.
Right.
And the angles are preserved. It turns out both those things, but. So, that's a little bit with ratios. Let's do a couple of proofs using this definition of division. That's why we need to use division properly, because we're going to be talking a lot about ratios, because we're going to be talking a lot about similarity. All related. So let's see. Definition 9.2 is the definition of division. We already have that up there. Theorem 9.2. If b is not equal to 0 and c is not equal to 0, then a over b is equal to ac over bc. Okay, so next thing I want to prove is that a over b is equal to a times c over b times c, where b is not equal to 0 and c is not equal to 0. So, quick proof here. Try and prove this is the case.
Why can't A be 0?
Because C's the
Why can't
same.
A be 0?
Right?
B can't be 0 because then we divide by 0.
Right.
C can't be 0 because then we're dividing by 0. Look, if you allowed C to be 0, then what we're saying is 1/2 is equal to 1/2 times the top by 0 times the bottom by 0, which is equal to
0.
1 times 0 is 0, 2 times 0 is 0, 0 divided by 0 is
Not defined.
undefined. So 1/2 is undefined. Now, so that's why C can't be 0 and B can't be 0. Okay, but you understand what we're proving here? If you have a fraction, you can multiply the top and bottom of the fraction by the same number, doesn't change it.
Right.
Okay, so wouldn't you just prove that by C would be equal to C, right? And then if you times that by C times B, if you times A by C and B by C, it'd be
It's not going to be as trivial as you think, because we're going to have to use this precise definition to prove this. You're used to using your rules, oh, you can cancel out C top and bottom. That's what we're proving right now, is that you can do that.
Right.
So you can't say, well, we know that. Yes, you can use that in your algebra courses, but you have to prove that before you can use it. So here's a proof for it. So let's see. Let x equal a over b. And my job is to prove that x is also equal to a times c over b times c. And then we're done, right? So whatever a over b is, we're going to call x.
Right.
I'm going to prove that that x is also a times c over b times c. Therefore, they're equal. That's a big picture of how I'm going to do this. You with me? Okay, so if x is equal to a over b, by definition, what does that mean?
Means that x is equal to
Don't get confused by how I'm using the x here and how I'm using it there. How I'm using it there is the z here.
Oh, therefore, right.
a. Therefore,
A
equal to
B times x. Perfect.
Yeah.
Now, we're going to go back and we're going to use a theorem of logic. I stressed this clear back when we covered logic because it comes up so much. But you probably don't remember. Going all the way back to logic, if I have something is equal to something, then if I apply the same symbols to both sides, so then A circle C is equal to B circle C.
Right.
For any operation
Reflect.
and for any C, as long as whatever we're doing is still well defined.
What's the term for that? It's not transitive, is it?
No. It's just a theorem of logic. That if two things are equal, then you can manipulate both sides the exact same way and it's still equal.
Right.
And that's what we're doing. Because how do we prove this? How do I know that this is true? Because I can now use our law of substitution. By definition, this is true. And then we use substitution to get to there. Substitution was one of our laws of identity. Our two laws of identity is everything's identical with itself, and equals may be substituted for equals. Those were our two laws of identity. So that's a theorem of logic that you can do an operation in the same term to both sides of an expression. It's more foundational than arithmetic. But you can for sure use it in arithmetic because arithmetic is built on top of logic. So now I can take this and I can say then A times C is equal to B times X times C. And if I'm being really proper, have to have parentheses like that. With me?
Yes.
Okay. Now I'm going to use something called commutativity, which means I can multiply in any order I want. B times X is the same thing as X times B. That's one of our axioms of arithmetic. So that's not something we prove, it's an axiom, it's a postulate. So A times C is equal to X times B all times C. Now I'm going to use what's called associativity, which means I can do the X times the B first and then multiply by the C, or I can multiply the B and the C together first and then multiply by the X. So the way we mark that is we say A times C is equal to X times B times C. With me?
Yeah.
Now I have a number is equal to X times a number. That is the exact definition of, well, we don't need the back and forth arrow. By definition of division, that gives us that X is equal to A times C over B times C.
Right.
You with me?
Yeah.
And there it is. If X is equal to AB, then it's also equal to A times C over B times C. And we can do all the logic in reverse to prove the other way. Well, if you started here, what if X is equal to that? Well, then going backwards, that by definition is that. Going from here to here using associativity, do, gets us to here. Then we use something we proved all the way back from our algebra review, which is that you can cancel out both sides, the same number on both sides, which gets us to there, and then finally to there. So going the backwards direction, there's actually a theorem that we use going from here to here. Going from here to here is logic, but if you want to undo it, that you can't necessarily always do. So that came from arithmetic. And so there's a full-blown proof. Okay, our next one here is A over B equals C over D if and only if AB equals BC. I don't know if we'll need to make reference to that at all, so we'll scribble it over here. So our next proof is that A over B equals C over D if and only if AD is equal to BC, where B is not equal to 0 and D is not equal to 0. Now this, you came across before, sometimes, well, I don't know if you necessarily saw it that way. So, we'll just go through. If A over B is equal to C over D, then A times D is equal to B times C. Sometimes they call that cross multiplying. You multiply these two numbers together and those two numbers together, and they're still equal. Okay, so that's what we're proving is the case. So let's go the forward direction first. Let's go this way. So assume A over B is equal to C over D. And I'm trying to get to, this is the case. Let's think. Assume A over B is equal to C over D. What is the best way to do this?
You're trying to prove that
AD is equal to BC.
that's what you're trying to prove?
Yeah.
We're trying to prove that AB is equal to CD if.
I'm trying to show that if this is the case, then this is the case. And then we'll do the reverse. So showing that if this is the case and this is the case, let me think. So assume that's the case, comma, let's just name one of them. And let X equal A over B. Well, then that would give me that A is equal to B times X. Let me think about this differently. Let's assume that's the case, 2. Then, let's just see what A times D equals. Then A times D is equal to maybe I'll have to solve for X and substitute out here. So, we'll come back to that in a second. Let me do what I was thinking up here. So, let's say that A over B is equal to C over D, and both of these, since they're both equal, we're going to call them both X. Whatever that number is. So then that gives me, since A over B is equal to X, that gives me A is equal to X times B. Right? Since A over B is equal to X by definition of division, that means A is equal to X times B. And since C over D is equal to X, that means C is equal to X times D. Okay, 2. Then, now let's see if we can figure this out. Then A times D is equal to, let's see, A is equal to X times B, right? So, this is equal to X times B times D. Now, this is equal to, just using associativity and commutativity, I can rewrite this as B times X times D. You with me?
No.
We'll just reorder these terms. Put the B first,
Right.
and the X and the D together.
Have this spread this out.
Good?
Yep.
Now, XD is C. So this is equal to B times C. Okay, that turned out to be pretty easy. So AD is equal to B times C.
Good.
So I showed if these two are equal, and we call them x, whatever they are, then A times D is equal to B times C. So I showed if this is the case, then this is the case.
Right.
Now I need to go the other way. I need to show if this is the case, then this is the case. Right? So let's figure out how we're going to do that way. So now assume A times D is equal to B times C. Okay, for then, let's see, A over B is equal to let's see, I can multiply top and bottom by the same thing and it doesn't change it, right? That's using what we did over here.
Right.
So I'm going to say that A over B is equal to A times D over B times D, right?
Okay.
So multiply top and bottom by D. Now what does AD equal?
BC.
AD is BC. So that gives me that B times C over B times D. Now, using this theorem again, if I have times the same number, top and bottom, I can cancel them out. So I can cancel out my B's here. And that gives me is equal to C over D. Okay, that was pretty easy too.
It's super simple, but it's kind of just like, what just happened?
Yeah,
you know?
this low-level proofs in arithmetic, you have so much intuition, it's almost hard to prove these simple little proofs. Because you're not sure what to use, where to go, what to do. There's nothing leading the way for you because you have so much intuition about it. But yeah, so there we go. Prove that little theorem. Last theorem is that A over B equals C over D if and only if A over C equals B over D. Okay. This one I don't even think we need to write out. Showing A over B is equal to C over D if and only if A over C is equal to B over D. In other words, if you swap the diagonal, it's still true. That's what we're trying to prove. You with me?
Yes.
Trying to show that this is the case if and only if this is the case. That's what I'm trying to show.
Right, you only swapped one thing, right?
Yeah, I just swapped those two. So that's what we're trying to prove.
Can you just swap those two?
Let's come up with an example.
Can we just plug it in with numbers?
Yeah. So I know that 3/9 is equal to, give me something 3/9 is equal to.
Equal to
6/18.
1/3.
So he wanted to do 6/18. We could have done 1/3. He wants to do big numbers.
It's not 6/18, I was wrong.
Oh.
Well, yeah, it is.
No, you're right.
That is.
Perfectly fine. Okay, so now let's swap those two.
We can do 1/3. Let's do
No, I think this is fine. Let's swap those two. So now 3 over 6 we're saying is equal to 9 over 18.
True.
That is 1/3, that is 1/3. Over here that is 1/2, that is 1/2. It still worked.
Right.
Try 1/3.
If we would have, you're saying, if this would have been 1/3? Well, if this would have been 1/3, and we would have swapped these,
Yeah.
then the 1 would be here, the 9 would be here, the 3 would be here. So 3 over 1 is equal to 9 over 3.
Which is still 3.
If 1/3 is equal to 1/3, then 3 is equal to 3. And if 3 is equal to 3, then 1/3 is equal to 1/3. Okay, so there's two concrete examples, that's what we're trying to prove. This one I'm not going to write out the full proof, I'm just going to use these previous proofs because now it's pretty obvious. So I'm trying to show that this is the case if and only if this is the case. Well, I know that this is the case if and only if AD is equal to BC. Right? That's using this. And now, this is the case if and only if I just swap my B's and my C's around. AD is equal to CB. And now, using it after swapping, that's the case if and only if this is the case. So since this is true if and only if this is true, and that's true if and only if that's true, and that's true if and only if that's true, then by transitivity, that's true if and only if that's true. So that one's pretty straightforward. Okay, so I think that was it for our touching on algebra. So a little bit of the algebra that we're going to be using for talking about proportionality for talking about ratios. So now we're going to be talking about similarities, similar triangles, and we're going to be talking about ratios and the proportionality between the sides somehow remaining the same. A little bit, just of a side note about this word ratio, just for the fun of it. Did we already talk about ratio?
Yeah.
Oh, we did?
Yes. I thought so.
Reasonable, it just means.
Yeah, okay. So, yeah, we won't bother with that.
Go back to the I got it wrong.
Okay, so our next definition. If A, B, and C, D are segments, what's the ratio between them? You can almost guess these definitions.
A, B, and C are segments.
So I've got a segment A, B, and C, D.
Oh.
What do I mean by the ratio of A, B to C, D?
AB over CD.
A, B over C, D? Almost. A, B over C, D. How do I take a segment and divide it by a segment? This is a set of points, this is a set of points.
Of AB.
It's the length of AB divided by the length of CD. Remember, the length of AB, now that's a number.
Right.
The length of CD, now that's a number. And so now we're talking about a number over a number. That's a ratio. So when we talk about the ratio of AB to CD, we mean this. We mean the length of AB divided by the length of CD,
So when there's a line
or
on top,
vice versa.
It means the length of segment. It
Yes,
doesn't mean
that means segment, and that means the length of the segment. So in the lines above, we're always talking about a number. We are no longer talking about a geometric object. We're talking about a number. So these are numbers. Everything we were proving here, this was about numbers, and nothing to do with geometric figures.
Okay.
Similarly, if I were to tell you that A, B, C, D, and E, F are proportional to A prime, B prime, C prime, D prime, and E prime, F prime, what does that mean?
Which also, well, it's the same as the other coinciding.
It means AB, the length of
So
AB is
AB
congruent to the, is
AB
over the length
A prime
The
B.
length of AB divided by the length of A prime, B prime
equals.
is equals, not congruent, equals. We're now talking about numbers.
Right.
Nothing to do with geometric figures. So that number divided by that number is equal to
This number.
AC over A prime. C prime's length is equal to, oops, not AC.
C, D.
CD. Jeez, that's what happened. CD's length over C prime, D prime's length
Yes.
is equal to EF's length over E prime, F prime's length. That's what we mean. Similarly, if I would have said that this triangle, if I would have said triangle, here we had triangle ABC is proportional to A prime, B prime, C prime. When I'm talking about the triangles being proportional to each other, I mean that length over that length is equal to that length over that length is equal to that length over that length.
Talking about length, not degrees.
Talk about their lengths.
When
That's what it means for one to, in some sense, be proportional to the other. So now we're ready for our full definition of similarity.
That's what a ratio is all about, proportions, right?
Proportions. Proportions are all about ratios.
So let's say you're,
Not ratios are about proportions. Proportions are about ratios. Proportions are communicated in terms of ratios. When I say these are proportional, I mean these three ratios are equal. Ratio, ratio, ratio. These three ratios are equal.
Right.
so like, for every, if your ratio is 3 to 1, for every 3 you get 1, and then, so 2.
Yes. So if the ratio of this was 1 to 3, then that would mean that this side length is 1/3 that side length.
Right. AB is
This
Yeah, yeah.
divided by that would have been 1/3.
Yeah.
In this case, it's more like 1/2.
Okay, yeah.
right.
Yes. So now the definition of what it means for two shapes to be similar. When I say that triangle, let's draw the symbol for it. When I say that triangle ABC is similar, so it's like congruent without the equals. It's just a squiggly. It's similar to triangle A prime, B prime, C prime. What am I saying? I'm saying that this, and this are true,
Right.
Their side lengths are proportional. Oh, sorry, not that one. I'm saying that in order here, I'm saying AB over A prime B prime, order matters. I'm saying AB over A prime B prime, obviously talking about their lengths, is equal to BC over B prime C prime, is equal to AC over A prime C prime. And angle A is congruent to angle A prime.
But I thought we can.
Angle B is congruent to angle B prime. And angle C is congruent to angle C prime. That's what it means for two shapes to be similar in general. So this, we were talking about triangles, so we only have 3 sides. If I picked a random 4-side shape and a random 4-sided shape, what it means for them to be similar is all their side lengths are proportional to each other and all their angles are congruent. It happens to be the case that with triangles, and we'll prove it, that if all their angles are congruent, then all these proportionalities also hold. That is the case with triangles.
So if
That isn't the case if we get to 4-sided polygons.
Right.
I think I understand.
So it has to be all these properties. All their side lengths have to be proportional, and all their angles have to be congruent for two shapes to be similar. Give you a quick example of two shapes that are not similar, but have all their angles congruent. All their angles are identical, yet this is not similar to this, because the proportionality isn't maintained. The ratio of this to this is not the same as the ratio of this to this. So if I were going to draw something similar to that, it would look more like this.
It can't be that angles are congruent to each other, the proportions have to be equal to each other.
As well, both angles and proportionality.
Is there a way
Right.
that the
4-side figure.
proportionality can be different and the angles aren't? Is there any possible way that that's even possible?
That what happens?
Where the proportions,
Are
the ratio,
it's to scale, but it doesn't have the
it's
correct
to
angles.
scale, but the angles aren't congruent. Is that even
Oh, you're saying we have all the proportionality, but we screw up on the angles?
Yeah.
I would guess yes, probably with some weird looking polygon, but I don't have one off the top of my head.
Well, yeah, actually, I think that it'd be a trapezoid, not a trapezoid, one that's slide.
Well, you can pick like some 7-sided figure, make sure the side lengths are there
No, on it,
with the
yeah,
angles
yeah.
and flip things
Yeah,
around.
okay,
a
deal.
rhombus?
You're saying we can see it with the parallelogram?
Yeah. Absolutely. You can just make sure that.
Oh, duh. He's absolutely right.
Yeah.
Okay. Good. Wonderful. So take this. Now take this exact shape. Imagine I made this with sticks, right? Right now it's similar to this, right? Now pull it a little bit. Now the angles are all skiwampus,
Yeah,
but the
so-
proportionality is still there.
Right. Yeah.
So yeah, that's an easy counterexample. Good.
The lengths are
So
still
they
the same.
both
they're just-
have to be the same.
So you need proportionality and you need angles. Okay, so I think we understand the definition of similarity. All right. Oh, I skipped a proof. Okay, so our next proof is, no matter what unit of length is chosen for measuring two segments, the ratio of these segments is the same number. Let's make sense of that for a second. So I think we can get rid of some of this now. So imagine, let's pick two actual real world objects. Imagine I'm talking about the length of this desk compared to the length of this room. So AB is the desk and CD is this room. So we're looking at AB over CD. A's right here, B's right here, C's in that corner, D's in that corner. With me?
Yeah.
Now, what we're proving is that this ratio comes out to the exact same number no matter what unit we choose.
Right. They should.
right? So, it's kind of hard because we don't have the exact numbers. So, rather than using this desk in this room, I'm going to pick something else. Let's say we're picking two distances, and AB happens to come out to exactly 2 kilometers. And CD happens to come out to exactly 5 kilometers. So then what's the ratio? Kilometers cancel out top and bottom, and you're left with it's equal to 2/5, which is just a number. The units should always cancel out, and you should be left with just a number. 2/5. Now that's if we measured it in terms of kilometers. What if we would have measured it in terms of meters? What's AB in terms of meters?
2,000 or 5,000.
2,000 meters, and this one is 5,000 meters.
Right, take out
Which
meters, take
meters
out
cancel out? Cancel, cancel, cancel. Left with 2/5. If we would measure it in terms of centimeters, inches, miles, if we would have perfectly calculated it all, it would always all cancel out, leaving us exactly 2/5 no matter what.
Right.
Right? So that is what we're proving. So, this one, a little bit hard to just follow with a picture, so let's actually write this one out. Proof. The ratio length of AB over the length of CD is a constant.
What does that mean?
It doesn't change. It doesn't depend on your choice of units.
Right.
Okay, so let's draw a picture here to help us think. So AB, here's AB, here's CD, and we're talking about AB over CD, whatever that number is. Now when we measure these things, we have to choose a unit. You with me?
Right.
Right? When I talk about the length of this room, I said this room is 7. True or false?
True.
7 what? You need the unit. So, I'm going to pick some unit. My first unit, I'm going to call EF. A, B, C, D. Yeah, EF is next.
So we're going back to our first.
And then I'm going to pick some other unit, GH.
That are proportional to each other, right?
Just 2 random units. So I'm going to show that this length divided by this length is the exact same number, regardless of if you're using these units or if you're using these units. Doesn't matter which unit you're using, this length divided by this length is always the same number. It's a constant. That's what I'm proving. Alright. So 1. Let EF and GH, I don't know why I did that lowercase, GH be units, comma, let AB equal M and CD equal N when using EF. So, when we use this as our unit, and we measure this, we get that this is M units, whatever M is. And when we measure this, we get N units, whatever N is. Whatever it is, we're going to get numbers. If this is our unit and we measure these, 2 numbers are going to come out, whatever those numbers are. Right?
Right.
3. Let X equal the length of EF when using GH. So now, when this is our unit, and we measure the length of this, we get that this has length X. You with me?
Yes.
So now, what is the length of AB using GH? If its length is M when we're using EF, what is the length of it when we're using GH? Let me go through a concrete example, then I think it'll be obvious. Let's say I'm measuring my height and I'm using markers.
Okay.
And we measure my height and it comes out to exactly 15 markers.
Okay.
You with me?
Yes.
Now I say a marker lid, there's exactly 5 marker lids in one marker. So if I'm 15 markers tall, how many marker lids am I?
Okay.
How many?
100.
So
You don't know. What's the proportion? What's the proportion to markers?
You do know. Answer the question.
5 times 15.
5 times 15, 75.
75.
Let's answer the question again.
What's your proportion for marker lid?
5. We already went over that.
Okay.
So I'm exactly 15 markers tall, and this marker is exactly 5 lids tall. How many lids tall am I?
75. 15.
5 times 15, 75.
75, yeah.
So if this segment is exactly NEFs, and EF is exactly XGH, how many GH is AB?
XM.
XM. It's just M times X. And times X for this as well. Now we proved that all the way back when we were talking about these lengths. But I want to remind you of that and make it click to your intuition. So 4. Then AB over CD is equal to M over N using EF, and AB over CD is equal to M times X over N times X, which is equal to M over N using GH. Regardless of which unit we choose, it always came out to exactly M over N. So, it doesn't matter what unit you choose, the ratio of 2 lengths is always the same.
Right.
So it's not dependent upon the units. So once you have a ratio of 2 lengths, that's a number, it's a fixed number. What's the number? Who cares? But it's a fixed number, it doesn't change. Your units don't matter. The ratio of 2 lengths is always the same. If I'm twice as tall as you, I'm always twice as tall as you. It doesn't matter what units you choose.
Right.
If I'm twice as tall as you using feet, you say, okay, but let's check in inches. Let's see if that changes anything. It doesn't change anything. Alright, so that was Theorem 9.5. So, definition 9.4. One segment is said to be commensurable with another segment if the ratio of the first number to the second number is a rational number. Okay, this is a weird idea. The idea of 2 lengths being commensurable, or common measurable, or it can be measured with common unit. 2 lengths being commensurable. What does that mean?
So they measured with common unit. Doesn't every single length be commensurable?
Right, so let's break down exactly what I mean. I guess I have these 2 things up here. Let's take these 2 lengths right here. So when I come here and I try to measure these maybe with inches, maybe this is exactly 17 inches, but this was 21 and some extra. So this one came out perfectly, this one didn't.
So they're not commensurable.
So, well, maybe not. So I say, okay, an inch didn't work. Maybe I'll use 1/100 of an inch, a really small portion of an inch. Right? And then see, this one still comes out perfectly, since inches came out perfectly, so 100ths of inches will come out perfectly. But will 100ths of inches come out perfectly on this? Maybe that doesn't work. So I pick a smaller unit. And I keep picking smaller and smaller units, trying to find that small unit I can use that perfectly goes into both of them.
But they all.
And maybe I come down to using the width of an atom. And I count the width of an atom for each of these and the width of an atom for each of these. The question is, can I always find a small enough distance so that it perfectly goes into both these lengths?
Yeah.
Yeah? No? We need a tiebreaker.
Coin.
No, you're the tiebreaker.
I'm the tiebreaker? I
Yes,
think
sir.
that no, you won't be able to find one.
You said no? Alright, no's have it. And the no's are correct. And that is a very surprising fact.
You'll never
It is.
find.
There is never a small enough length that you can use so that you can perfectly measure both of these things. It was very surprising when the Pythagoreans first stumbled across this. this sharp now.
That's right.
What is right? The way that they came across it is on a square and looking at its diagonal. So
And how do you know anything's equal to? Or how do you know what's proportion and what's not?
what's proportion and what's not?
Like you said, you could find something that goes in to both of those, but you can't. Right? That's
So-
what you said.
So we say that two things are commensurable. I gave you intuition for what it means. You can find a small enough unit that can measure both of them. That's what it means for them to be commensurable.
Right.
Its precise definition is two things are commensurable if their ratio of their side lengths, AB over CD, is a rational number. So this is a number if it's in the rationals. Remember what the rationals are? Set of all possible fractions you can think of. Or a decimal with a repeating pattern in the decimal points. Those were all rational. And so I went over proof back when we first talked about this, how a number like 21.379 repeating is rational. And I showed you how to find the rational number that turns into. So rational, any number that can be expressed as a fraction, that's a rational. So if this can be expressed as not as a fraction, but as an integer over an integer, a whole number over a whole number, then these two things are commensurable. That's the definition. You with me? All right. Now, I told you that the Greeks figured out a long time ago that you can find two values that are not commensurable. That you can't find a unit to go into both of them. And they did it with the square. If I've got a square here, and this side length is 1 unit, what is the length of the diagonal? So that's 1, that's 1. What's the length of the diagonal?
It's isn't it like
It's 1.
That's definitely a longer
It's 2.
distance than that.
It's 2.
It's 2?
It's like
No.
2 would be if I pulled those straight out like that.
I don't know. It's a squared plus b squared equals c squared.
So go through that.
A squared is 1.
1 squared plus
1 squared,
equals the value we're looking for.
which is
1 x2, which is
So we'll call x squared, right?
yeah,
which is 2
What's 1
squared.
times 1?
1.
Woo! 1 times 1.
1,
Add them together.
2.
2. So 2 is equal to x squared. So x is equal to
Square root of 2.
square root of 2.
yeah.
You guys,
Oh yeah.
look at the picture. For heaven's sake. This is not 1. This is not 2. This is not 4. You instantly know it's about 1.5-ish. Somewhere around there. We call that a sanity check. Are you even sane in your answer? 2's insane. 4's insane. 1's insane. Let's give sane answers. And the answer is root 2. Which is 1.7 blah blah blah, whatever it is. Okay, so what the Greeks found out early on is that the square root of 2 is an irrational number. You can't express it as a fraction. So if I'm looking at my ratio of root 2 over 1, that's the ratio of this side length to this side length, that is not a rational number. That is an irrational number.
Right.
And so that side length and that side length are not commensurable.
Commensurable.
And so there is no small enough unit you can use to measure that perfectly goes into this and perfectly goes into this, which is astounding. And at the time, do a little bit of history here, at the time the Greeks didn't have a notion of an irrational number. For a Greek, a rational number and a number are one and the same thing. And so the way the Greeks thought about this is that this isn't even a number. They thought that the ratio of this side length to this side length isn't even a number. That's the way they thought about it. It took a leap forward to, let's just call it root 2. But they said, that's not even a number. So this is why the Greeks went with geometry. This is the reason Greeks developed geometry so much with no numbers involved. It was weird, they thought. Somehow I can easily talk about distances that aren't even numbers. And so in some sense it seemed like geometry was more powerful than arithmetic. It can talk about values that arithmetic can't even talk about.
Right.
That's the way they thought about it. And so that's why when they developed their algebra, they're doing everything geometrically. It seems like you can do more with geometry than you can with arithmetic and with algebra. That's the way it appeared to them. And this is why, or one of the main reasons why. So that's why they don't have numbers all over in their geometry, and they prove everything just geometrically. No numbers involved. Okay. So that's what it means for one length to be commensurate with another one, is that their ratio is a rational number. Okay. Our next theorem. If two segments A, B, and C, D are commensurable with, two segments A, B, and C, D are commensurable with each other if and only if there is a segment, EF, which is used as a unit of measurement, makes A, B, and C, D whole numbers. So, let's, this was probably worth writing out as well. Hard to follow what's happening with just a picture. So, theorem, what theorem are we on?
Theorem.
I'm actually not sure.
I don't remember.
Theorem 9.6. You guys aren't following along? Theorem 9.6. I'm going to say that AB is I don't think that's right. Yeah. Is commensurable with CD if and only if there exists some segment EF such that the length of AB is equal to M, the length of CD is equal to N, comma, where M and N are integers, or in other words, whole numbers. Alright, what are we saying? AB is commensurable with CD if and only if I can find some unit of length, EF, some unit, such that EF goes into AB exactly M times, and EF goes into CD exactly N times, where M and N are integers, they're whole numbers. So there's no remainder, it goes into it evenly. That's the case if and only if AB is commensurable with CD. So that's what we're proving. Let's do the forward case first. So I'm going to assume AB is commensurable with CD and show that that's the case. So assume AB is commensurable with CD means that their ratio is a rational number. So assume AB, its length, over CD, its length, is a rational number. What does it mean for it to be a rational number?
It means for it to be a number that has or has a man.
What's a rational number?
It's any fractions.
It's a fraction, not any fraction. This is not a rational number, root 2 over 1. It's a fraction.
It's a fraction that contains real numbers.
Not real numbers,
It's
that's a
something
real
that
number.
is repeating. It's a decimal that repeats.
A repeating decimal happens to be rational. We prove that by showing it's rational.
Something that can be reasoned.
It's rational if it can be written as a fraction of integers or whole numbers. This is not rational. 2 over 1 is rational. That's an integer, that's an integer. Square root 2 is not an integer. Right? Okay. So if this is a rational number, then that means that there must exist two integers, m and n. There must exist, have I used that symbol with you guys before?
Yes.
Okay, so then there exists m and n in the integers, such that AB over CD is equal to m over n. That's what it means for it to be rational. It can be written as an integer over an integer. Okay, 2. Now I am looking for the unit of length. I need to prove that there exists some unit length EF so that AB is exactly M of those and CD is exactly N of those. What is my unit length going to be?
M times N?
Can it be?
No.
Yeah, just a guess. I think it's right.
I need to find a length now of EF so that the length of AB is exactly M and the length of CD is exactly N.
So it would be
AB divided by M.
AB over M, the length of
C
AB,
over N.
you've got the right idea. So let EF be any segment such that EF is 1/mth of AB. So make EF 1/mth of AB. Three. Then what's the length of AB?
AB is so the length of AB
1/n.
is
No,
no.
it's MM.
It's M 1/nths. Or no, still
M-
off right there. Sorry.
MM, right?
EF is our unit.
Yeah.
EF is
Yeah.
1/mth of AB.
AB is MMs of EF. No. No. Crap.
1M.
You are right.
So MMs is
AB
equal
is-
to AB.
How many EFs is there in AB?
1
MMs. Right?
Look, EF is 1/mth.
It's M.
Look, if we picked
There's
a
N.
stick,
It's N.
yeah, if we picked a stick that was 1/3 the length of this room, how many sticks can we fit in the room?
3.
3. If we
Yeah.
pick a segment that is 1/mth of AB, how many EFs can we fit in AB?
M.
M.
Yeah.
That's what we mean by the length of it. When we say the length of AB is M, we mean it's M of our units, M of our sticks.
Right. It's how many?
So we chose our unit so that the length of AB would come out to exactly M.
Yeah.
You with me?
Yeah.
Because all we knew before is that the ratio of AB over CD is M over N. We did not know that the length of AB was exactly M.
Right.
We just knew that its ratio was this, because the ratio doesn't depend on the length. The ratio is a ratio regardless of the unit we use.
Right.
We happened to choose a unit that made it come out to, the numerator come out to exactly M.
Right.
Now, if this is our unit, what's the length of CD?
CD.
Yeah. So I know the length of AB is M. Does the length of CD have to be?
CD is N.
And CD is equal to,
N.
has to be equal to N.
Yeah.
Because if this comes out to exactly M, the only way for this to still be equal is if CD is N. So we did it. What was our job? Our job was to find some segment, EF, such that the length of AB was an integer number of EFs, and the length of CD was an integer number of EFs. So we did it. Now we gotta go the other way. So 4. Now, assume that there exists EF such that the length of AB is equal to M, and the length of CD is equal to N, where M and N are integers. 5. Then let's look at the length of AB over the length of CD. The length of AB over the length of CD is equal to what?
Is equal to M and
M over N. Is M over N a rational number?
yeah.
Yes.
How do you know?
Oh, no, we don't. No, that is. Oh,
So is this a rational number?
Yes.
How do you know?
Because we made one.
Because it's an integer over an integer. That's what it means to be rational. An integer over an integer. So this is a rational, which is the exact definition of AB being commensurable with CD. It means the ratio is rational. So that gives us that AB is commensurable with CD. So we show that this definition of commensurable, then being a rational number, gives you what I was trying to establish as your intuition for commensurable. What does it mean for two lengths to be commensurable? It means you can find some unit small enough such that it perfectly goes into both of them an integer number of times.
Right.
Now we proved that that was the case. So we proved that the way we intuitively think about it is a valid way to think about it. But the exact definition of AB being commensurable with CD is the ratio is a rational number. Make sense? All right. Hang in there.
Everything makes me angry.
So let's move on to our next proof, Theorem 9.7. If the angles of one triangle are congruent respectively to the angles of another triangle, then the triangles are similar. All right. So this is the notion that we already had intuitively for two triangles being congruent or similar to each other.
Eat a cup of coffee. Sorry.
So what are we trying to prove?
That's how these are. Don't you forget Jackie. Helps. This one like espresso. Doesn't taste it. You need a cup of coffee?
All right, let's look at this. Here's what we're trying to prove. We're trying to prove that if this angle is congruent to that angle, and if this angle is congruent to that angle, and if this angle is congruent to this angle, then these two triangles are similar. So what do I need to prove? I need to prove that this length over this length is equal to this length over this length is equal to this length over this length. I need to prove all their sides are proportional to each other. So I need to show that if the angles are proportional or are congruent to each other, then all the sides are proportional to each other, and therefore these two triangles are similar. Remember, that's what it means for two shapes to be similar. All their sides are proportional and all their angles are congruent. We're going to show in the special case when you have triangles, all you need to know is that their angles are congruent. And you get that the sides are proportional for free. That's what we're going to prove. Do we understand what we're trying to prove? Okay. Now we're going to cheat a little bit in this proof. We are going to assume that the side lengths are commensurable.
Okay.
Because dealing with the case where they're not commensurable requires us to use limits or to use area. Neither of which concepts we've talked about yet.
Right.
We'll get there. So there's a second way to do this proof that's pretty elegant using areas. Areas is next chapter. You kind of need limits to talk about areas. So unfortunately, we're just going to have to deal with the case where they're commensurable. So we're going to assume that A prime B prime over AB, its lengths, can be written as M over N, where that is where M and N are integers. So that's something we're going to assume, and we're only going to prove that this works in this special case, but we're going to pretend after we prove that it always works, because it does always work. but we're just proving a special case.
Okay, so one more time. We're proving.
So we are going to prove that if two triangles have all their angles congruent to each other, then the two triangles are similar.
Okay.
We're going to limit ourselves to only proving it in the case where the side lengths are commensurable.
Right.
Not because it's only true in that case, but because handling the other case
It's very hard.
uses limits or uses area, neither concept we've talked about yet. Okay, so there's an assumption that we're going to make that's not really warranted, but we're going to do it. Okay, so how are we going to do this proof? First thing I'm going to do is I'm going to come and I'm going to mark a point down over here. ABC, we'll call this a point D. And I'm going to choose that point so that this side is congruent with this side. You with me?
Yes.
And then I'm going to come and pick a point over here, call it E, and I'm going to choose it so that this side is congruent with this side. Perfectly valid choices.
Right.
All right, if I choose it that way, then this triangle I make up here is going to be congruent to that triangle.
From side angle side.
From side angle side. So now if I can prove that this triangle is commensurate with this triangle, or sorry, if I can prove this triangle is similar to this triangle,
Then you got it.
then we've got that this triangle is congruent to or similar to this triangle. So that's what we're after here. So again, erase that angle now since it's taking up a lot of space. But we see that this triangle is congruent to this triangle, so now we're working with this triangle in this picture. With me?
Yeah.
Okay. Now, since A prime B prime over AB is equal to M over N, I know that, then I know that this distance over this distance is the same. I know that AD over AB is also equal to M over N. If this distance over this distance is equal to M over N, then this distance over this distance is equal to M over N. Because that distance and that distance are the exact same value. Turns out that's what it means to be congruent. Not what it means to be congruent, but we get that for free from congruence. If things are congruent, they have the same length. You with me so far? So, that means that there exists some length I can use, such that this is exactly M of those lengths, and this is exactly N of those lengths.
Right.
So, that gives me that there exists a unit such that the length of AD is equal to M, and the length of AB
N.
is equal to N. So we can mark off each of those points. I'm going to draw it so that M happens to be 2, and N happens to be 3. I'm going to try and get that from my picture. So we can break it off into those lengths. Break this up into N pieces, which will also break this up into M pieces, all using the exact same length. You with me?
Yeah.
Okay. So now, what do we do?
Now we gotta do the same thing to the other side.
Maybe we're losing track of what we're trying to prove here. I'm trying to show that the small triangle is similar to the big triangle,
Right.
which means I need to show that AD over AB, whatever that is,
Right.
is equal to AE over AC, which is also equal to DE over BC.
Right.
I need to show that all those are proportional. Now I'm just going to show that AD over AB is equal to AE over AC, but showing how this is also equal to this, same proof again.
Right.
Okay? So I'm going to prove that AD over AB is equal to AE over AC. So I need to argue, essentially what I'm trying to argue, is that the length of AE over AC is equal to M over N. If I can get this, I'm done.
Are you trying to argue that E is the bisector, the bisecting point?
Nope, it doesn't bisect it.
No?
Nope, it's just another triangle. I'm trying to argue that this triangle is similar to this triangle.
No. Okay.
Which means I need to argue that all its angles are congruent,
Right.
which is one thing,
And also that all its sides are congruent.
and also that all of its sides are proportional to each other.
Right. Proportional. Right. Not congruent.
Proportional. So I know that AD over AB is equal to M over N. I need to show that AE over AC is also equal to M over N. That's how I'm going to show that they're proportionally the same.
Right.
You with me?
Yes.
Okay, so what are we going to do? So I already marked off my end points over here. I know that the length of AD is equal to M and the length of AB is equal to N with some unit length. Right?
Yeah.
So I use that unit length and I mark it off. So I'm marking off the segments over here. I split AB up into those N segments,
Right.
which will also perfectly split AD up into M of those segments.
Right.
Whatever the unit is. I know some unit exists. In my picture here, I pretended that my unit was that big.
Right.
But it doesn't matter what the unit is. I just thought there is some unit out there.
Right, that is M and N.
Okay. Think we're on the same page here.
Yes.
Now, from each of those points, I am going to draw a line parallel to this line, parallel to the base, to the other side.
Okay.
So, that gives me this line comes over here, hits over there. This line is going to be that same line, hits over there. This line hits over there. And this line hits over there.
Right. All those are congruent to each other.
All those are parallel to each other.
Parallel, right, and all the spaces on
Oh,
AC
right.
are congruent.
Now, using our first theorem, I know that this is congruent to this, is congruent to this, is congruent to this, is congruent to this.
Right.
Exactly right. So I now know that this segment is congruent to this segment, is congruent to this segment, is congruent to this segment, is congruent to this segment. Because all these ones over here were congruent. That was congruent to that, was congruent to that, was congruent to that, was congruent to that.
Right, because the very first one we did.
Perfect. And so, what do we get?
That AE is M and EC is N. Or was that backwards?
You said
Oh,
it exactly
right.
right. AE is M
Right.
of those units, and AC is N of those units.
Right, they're not necessarily the same length as the other unit.
It's
but
not the
they're
same
still-
length,
They're still
but
M.
the ratio comes out the same.
Right,
And the ratio doesn't care about your unit length.
right.
And so then we see, perfect, that AE over AC is equal to M over N. Now I could have instead did my lines parallel to this, to AC, so did my lines coming down like this,
And done BC.
and done BC, and it would have been the same thing.
It would be the same thing, which you would have to do in order to finish.
So,
right.
yeah. So then AD over AB is equal to AE over AC is equal to DE over BC. Right?
Right.
And I don't know if we argued that all the angles are the same, but since we're talking about parallel lines, that line's parallel to that line, so this angle is the same as this angle.
Well, we know for a
this
fact
angle
it's
is
the same angle.
the same as this angle, and then the top angle is the same as the side.
We know that they're the same angle because A is congruent to A prime, and
No, I knew that that angle was the same as that angle.
that's what I'm saying.
Okay. Yes.
And
Perfect.
we knew that ABE was congruent to triangle A prime, B prime, C prime.
That's a better way to say it. Okay. So without having to draw on it, I knew all those angles were already congruent to all those angles, but that triangle is congruent to that triangle, so we got it.
Right.
Perfect. So I have all that's the same, and I had, which gives me then that AD, this distance, is identical to A prime B prime.
Right.
So just replacing that, so I have A prime B prime, its length over AB is equal to, what was AE congruent to?
Congruent to A prime C prime.
A prime C prime over AC is equal to, and what was DE?
BC.
B prime C
B prime C prime
Oh, right.
over BC. So I have all those are proportional, which means all these are proportional.
Right, so those two triangles.
And,
Right.
like we already said, and angle A is congruent to angle A prime,
B.
angle
B
B
prime,
is
C
congruent
is C
to
prime.
angle B prime, and angle C is congruent to angle C prime.
Right.
Therefore, triangle ABC is similar, not congruent, is similar to triangle A prime, B prime, C prime. Okay.
So that proof is basically the exact same proof you would use for any triangle.
So from here on out, that's what we would use to see if any two triangles are similar. We just say, are their angles the same? And in fact, quick corollary of that, I don't know if the author bothers stating it, but we really only need to know that two of their angles are the same. Let's think about that for a second. See why that is. So imagine I have these two triangles, and I know that this angle right here and this angle right here, I know that's 60 degrees, that's 60 degrees. And I know that this angle right here and this angle right here are both 50 degrees.
And we know for a fact that the last one has to be 70 degrees.
Then we know for a fact that the last one has to be 70?
Yes.
Yes. 70 degrees. Because the angle sum of any triangle is a straight angle.
Degrees, which is
180 degrees, and this concrete takes but a straight angle.
Yeah.
So since the angle sum of any triangle has to be a straight angle, if two of the angles are the same, then the remaining angle has to be the same.
Right.
So you only need to know that two angles are congruent in order to know that two triangles are similar. Make sense?
Yeah.
So that's a quick corollary of that. I don't know if the author states it explicitly, but there it is. So let's see our next one, theorem. A line that divides two sides of a triangle proportionally is parallel to the third side.
What is this? 8.
This is theorem 9.8.
Did you skip 9.7?
Did I?
Oh,
I don't know.
That's one graded. I'm sorry.
Yeah, 9.7 we just did. Okay, so we're on 9.8. So 9.8, we got some triangle here.
Should be able to go all the way to 9, 10.
A, B, C. We've got some triangle here. And we want to show that if,
All check her name.
So far, we're gonna be on. We're gonna finish 9 today. It's my end. Yeah, I wrote it in 2 weeks. 14 things, and each one has.
we want to show that if
You might know those too.
AD over AB is equal to
This is 9.
AE over AC, then DE is parallel to
Very similar. It's in
BC. I think that is what we want. Okay, so here's our picture. We want to show that if these two if these two ratios are equal to each other, then DE is parallel to this remaining side. You with me?
Yeah, we did that with bisectors earlier.
Yes. Similar proof with bisectors. Now we're proving it didn't have to bisect it, it just had to cut it proportionally.
Right.
And we're going to do the proof almost the exact same
AE
way.
has to be proportional to AE.
Yeah, so I know that.
The proportion between AD and AB has to be the same proportion as AE and AC.
Right. So we already know if I have this line cut it exactly in half, we're good.
Right.
But what if I would have cut it exactly off the top third, or the top fourth, or the top 2/5, or whatever?
Yeah.
As long as it's proportional cut on both sides, turns out this is parallel to this. That's what we're proving. So we're going to do the proof similarly. I may come here and I'm just going to make the line that's parallel. And it's going to come through a point F. I need to argue that F and E coincide.
Right.
That's the argument. All right. So now, since this is parallel to this, then,
Hi, Julian is excused at 11.
all right, thank you. All right. Since this is parallel to this, notice that this line right here is a transversal. So this angle is congruent to that angle. And now A is congruent to A for both the small triangle and the big triangle. So the two triangles are similar.
Okay. Yeah.
Side to side. No. They're similar, right, because there's two angles.
They're similar because there's two angles. All right. So now that means that since this is a similar triangle, I know that AF, I know that this triangle, the green one, is similar to the big one.
Are we proving that E is parallel to C?
I'm trying to argue that this line, yes, is parallel to this line.
Right now, we're assuming that those lines are similar, and that's how we're proving that.
No. Okay.
That's literally what we're saying.
So then triangle ADF is similar to triangle ABC.
Because F is parallel.
Yeah, F is the one we constructed using the parallel line. So we do not know that ADE is similar.
Now we're showing that E and F are the same point.
Right, our goal is to get F and E are the same point and then we're done.
Okay.
That's what we're after. So now, since these two triangles are similar, what do I know in terms of proportionalities? I know that AD over AB, AD over AB
is
equal to, I can pick whichever ones I want,
AE.
AF,
Oh,
AF over AC.
Right, we're not using E. Right, we're showing the E and F are the same point.
But I already knew that AD over AB was equal to AE over AC. So I already knew that this was equal to AE over AC.
Therefore, F has to be E. Boom.
Therefore, this length has to equal this length. Therefore, AE is congruent to AF. Therefore, E and F are the same point.
Right.
Make sense?
Yeah.
Okay. So that was 9, what was that, 9-8?
Yeah, that's not it.
9-9. Given triangle ABC and A prime B prime C prime with one angle congruent and a proportionality, then the side lengths are congruent. Okay. So here's another interesting one. This one says we don't even need to know that two of the angles are congruent. I know that if I know two angles are congruent, then two triangles are similar, right? This one is going to say if you just know an angle and a proportionality, then you know the two triangles are similar.
So you're saying you have one angle and one proportionality, and you know.
Yeah. So here's what we're arguing. There are two triangles. So I have my triangle and my smaller one. Call this ABC. ABC. Call this
A prime, B prime.
A prime, B prime, C prime. Okay, so it's given to me. So what our given information is
A is congruent to A prime and AB is congruent to A prime.
oops, angle A. Angle A is congruent to angle A prime. And then which proportionality?
AB and A prime C prime. AB and A prime.
So
B
A prime, B prime. I like to do my primes on top. I know he does it the other way. A prime, B prime over AB is
Why
equal
like-
to.
Why did I do prime on top? Just because.
My gut wants a smaller number on top. And then was the other one AC? A prime, C prime over AC?
Yeah, I'm just kind of coming up with it.
Okay.
Yes, it was.
Oh, I think
Yeah,
it
it was.
okay.
100% was.
So that's our given information. We're trying to show that these two triangles are similar. Wonder if I have an added marker in here.
Trying to find one.
Alright.
Wow, that's neat.
Okay. So ultimately trying to argue that this triangle is similar to this triangle. Okay, gonna do a similar thing. Let's write our given information. I know that that is that. Alright. I'm gonna do the same thing. I'm gonna mark a point over here, call it point D. I'm gonna mark it so that this length is congruent to this length.
Right.
And I'm gonna mark a point over here, E.
That A prime, C prime is congruent to A.
Exactly. And so now I've got this triangle is congruent to this triangle.
Now we prove the M and M.
Perfect. So if I can prove that this triangle is similar to this triangle, then we're done.
Right.
Now, let me think how I am going to do that.
Wait, what else is given? Is that all it's given?
No, I haven't used this information yet. So this information, just rewriting out this information, this gives me that AD over AB is equal to AE over AC. So I still have that information that I need to use somehow. Let me think. What was our previous theorem, just barely?
9-8.
Yeah.
It's the one where we're showing an F.
Given that with an angle, what theorem are we proving right now? We're proving 9-9.
Yeah.
Okay, so let me think. Oh, duh. Our previous theorem just barely proved that
All you need is two angles.
if you cut this proportionally on both sides, then the line that cut them is parallel.
Oh, right.
So then DE is parallel to BC because it cuts them proportionally. That's what this says.
Right.
So since it cuts them proportionally, then this line is parallel to this line.
You see, like we just barely learned. Right. Okay.
And now I get, okay, now this angle is congruent to this angle. And so this triangle is similar to this triangle. This is congruent to this, so this triangle is similar to that one. You see that?
Yeah. That was quick.
So it just came down to arguing that that was parallel, which is what the previous theorem was all about.
Right.
Okay, so that was almost a corollary. That came almost for free.
Yeah.
Just have to stop and think about it for a second. Lost my page. That was 9-9?
Yeah, we're on 169 page. There, 9.
Okay, so 9-10. If the sides of one triangle are proportional to the sides of another, then the triangles are similar. Okay, so now we're not going to be given any angle information. We're just given all the proportionalities. So this time what we're going to be given, clean up my picture here some. We'll just redraw. So this time what we're given is, if I've got my triangle here, and our other one here, this is B, this is A, this is C, this is C prime, this is B prime, this is A prime. Okay. So this time, what's given to us is that A prime B prime over AB is equal to A prime C prime over AC is equal to B prime C prime over BC. All lengths. So I'm given that all the side lengths are proportional. Our job is to argue that this triangle is similar to this triangle. So now I need to somehow argue the angles. Okay, so let me think about this one. I'm going to do the same trick here. I'm going to come and pick D over here. D, so that's congruent to that. I'm going to come pick E over here. So that is congruent to that.
And where DE is congruent to BC prime.
And make a triangle here.
Prime.
So I don't have this is congruent to that necessarily.
Because you don't have the angles or what?
No angles, right? No
We don't
angles.
have any angle information.
So you wouldn't be able to find D is congruent to DE is congruent to B prime C prime.
Yeah, I don't have that yet.
We have side.
I think I'm somehow not yet.
I did. B prime is congruent. B prime C prime is congruent to DE.
This is congruent to that, and this is congruent to that. But I do not know that this angle is the same as that angle.
Don't we know that B prime C prime is congruent to DE?
No.
Right.
I picked a length on here that was this long, and I picked a length on here that was this long.
Oh, so because we don't know that A prime is
Right, this ABC triangle could have looked something like this.
Right.
And I just took that length, marked it here, took that length, marked it here, and made a triangle.
Right. It's not real.
Right. So far we do not know that that is the same as that. But we'll connect this triangle to that one later. I'm going to worry about arguing that this triangle is similar to this, and then we'll argue it's congruent to that. But let's see what that gives us. At the very least, since I have these, then I know that
AD is congruent.
AD over AB
And
is
AE over
equal to
AE over AC.
AE over AC. Like that. So then, DE cuts this proportionally, which tells me that the line DE is
Parallel.
parallel. So I know that this is parallel to this.
Now we know that angle B is congruent to angle D.
So now I know that angle is congruent to that angle. And I know that that angle is congruent to that angle.
And you know,
So that
angle-
gives me
And you know,
triangle
angle A is congruent to angle A.
ADE
Yeah,
is
not
similar to triangle ABC.
Not angle A prime.
Okay, so we still need to argue that this triangle is congruent to this triangle. Right?
We actually don't have to, but yeah, that's just what we want to do.
Well,
Huh?
It's not part of the proof. But
Yes, I need to argue that this triangle is similar to this triangle. I've only
Oh,
argued that
right.
this one is similar to this one.
right, we need to prove that those are not congruent.
So if this is congruent to this, then similarity holds. All I've got so far is that this small triangle is similar to the big triangle.
Right.
Okay, but that actually gives us the last piece of information that we need. So then I know, since this triangle is similar to this triangle, then I know that DE over BC
Proportional to BC.
Yeah. is also equal to, pick one of our other ones, doesn't matter,
AD over B, AD.
AD over AB. But AD over AB, I know, is equal to, rewrite it out with the primes just so that we can see it. This is the same as A prime B prime over AB, right?
Right.
And I know that A prime B prime over AB is equal to B prime C prime over BC.
Therefore, we know that B prime and C prime, B prime C prime is congruent.
Almost gonna do,
No.
Oh, right.
E.
Right,
Oh, yeah.
that's
right, so looking at this and this. The
Right.
first and the last gives me that
DE is congruent to B prime C prime.
perfect. DE is congruent to B prime C prime, which gives
Therefore,
me that the triangles.
ADE is congruent to triangle
And
A
now we
prime.
have angle side angle. And
Right.
also side angle
Side angle side.
No, that's by side.
Oh, side.
Right,
Side, side,
there's no, we have no
I knew that
angles.
this side was congruent to that side. I knew this side was congruent to that side.
We have
Finally,
no angles on A prime. C
those, so I
prime.
know by side that this triangle
Side.
is congruent to this triangle. This is congruent to this is similar to this, therefore this is similar to this.
Right, yeah.
And
We
that's
have
how you
no
finish that
angles
out.
on A prime, B prime, C prime.
Yeah.
That makes sense?
Yeah.
Okay, so we've done all our different possible combinations of information you can have to show two triangles are similar. You can either know that the side lengths are proportional, or you can know that the angles are congruent, or you can know an angle and a proportionality.
Right.
And with any of that information,
You can prove they're similar.
you know that the triangles are similar. You can prove it, and so now you can use that fact in whatever your homework problems are. That was 9.
10.
So what's gonna be homework? 9, 10, 9, 1, 2, 9, 10.
Oh yeah, he's got a ditch.
You got a ditch? Oh, but we're basically done. So I'm just gonna finish up chapter 9 because we only have
Chapter 9.
3 more proofs, but they're all closely related.
No, we don't. We have way more than that.
So
We have.
you go on chapter 9. I'm not sure why I signed on the syllabus.
You only signed half.
So yeah, get through the first half. It's okay if we get a week behind homework versus lecture material. I'm okay with that. All right, but
So
yeah,
you're gonna finish the section with lectures and then
I'm gonna finish right now because we only have a little bit more to do.
What's
We're
homework?
basically done.
We
Whatever's on your syllabus. First half of chapter 9
have to set 9-7. Yeah.
through 9-7.
Through 9-7.
Okay. So continuing with,
Where are we? We rated 9-10.
Alright.
that was if the
We have
side of one
9-11,
triangle is proportional to the side of the
We have
other.
4 more proofs.
So 9-11, the altitude. Okay, this is just such a cool proof, and it's so easy to see.
I gotta get going.
All right.
Alright.
erase some of this. All these are related to the Pythagorean theorem, which is why I'm just going to go through them all. Okay, so start with a right triangle. This is meant to be a right triangle with the top angle a right angle. That's what I'm trying to draw.
Okay, gotcha.
I'll label it. So angle A is meant to be a right angle, and then we have B and C. Now I'm going to drop an altitude down. An altitude
It's perfect, right, perfect, what is it?
it's a line that it makes perfect right angles with the opposite side.
It's perfectly wrong.
So that is a perfect right angle. And I'm going to mark this point down here that it makes A, B, C, that's point D. Now, you see how it split this right triangle into two smaller right triangles.
Right.
I'm going to draw each of those smaller right triangles down here just to help with clarity of the picture. So redrawing this right triangle, I'm going to draw it down right here. Might be a little off, but good enough that you can see what's going on. So that's point D, this is point A,
Right.
this is point B.
Right.
Draw this right triangle, give us a little bit of space, so it'll be over here.
And you're trying to prove.
So that's point D, that's point A, that's point C.
And you're trying to prove.
Here's what's amazing. I think this is one of the neatest theorems there is. When you drop this altitude, these two right triangles that it makes, so notice I now have three right triangles. This right triangle, and the initial one.
They're similar.
They're all similar to each other.
Right.
That's what we're going to
super
prove.
easy. That's super easy proof. Because we know that they're both we know that AD is congruent to AD, and we know that D is the right angle.
How do we know the top one's a right triangle? Where?
A was
So
when
this
we
one, by
constructed-
construction, that's a right angle.
Right.
Okay.
So I started with the right triangle,
We
dropped the altitude down.
and then it's super easy.
Okay, yeah, I think he sees it all, but let's just make sure we're seeing it. So this angle right here is the same as this angle right here, right?
Right.
So this is similar to the big one because right angle, 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 and so this remaining angle has to be this remaining angle.
Oh, they're similar to each other and the angle. They're similar to each other and the original.
Right, so this is just a scaled up version of this triangle.
And
Similarly,
that other one is
look
too.
at this one. This is a right angle, which we have a right angle right there. This angle is obviously the same as that angle, and so this angle has to be as big as the remaining angle.
That's cool.
That's cool. It's definitely cool. Yeah.
Yeah.
We also know we didn't even use sides yet.
Right.
We obviously know that AD is congruent to AD.
So just by looking at the angles already, yeah, it just pops out at you from the picture. That's what I'm saying, real easy to see. That's what makes it so neat. It's something so surprising that's so easy to see when you see it.
Yeah. We also know that AC is AC.
So now,
So
You can do that. Yeah. You can do that
both
without.
those triangles are proportionate triangles to that one.
yes,
And
all the
each
side
other.
lengths are proportional. So I'm gonna mark some side lengths on here really quick. I'm gonna call this distance right here X, this distance Y, and the height Z. So this is X, this is Z, this is Z, this is Y. So I know that there's these proportionalities. So I know, looking at this triangle, I know the small side goes to the medium side, small side goes to the medium side, as the small side goes to the medium side.
Oh.
You with me?
Okay,
It's
yeah.
pretty.
So yeah, this gives you similar triangles. It encodes so many relationships. It's amazing.
That's amazing.
And so all these side links are related in all sorts of ways. I also know that the small goes to the medium as the small goes to the medium up there.
Right.
So if this were A, if we called that A, if we called that B, and then X plus Y, all together we call that little c. Then I also know, for example, X goes to A, X goes to A would be here, B would be here. Small side goes to hypotenuse, as small side over here, small side is A, goes to hypotenuse.
B. Oh, C. Right.
C is the hypotenuse of the big one. And so you get, there's tons of relationships that are captured here, but I just want to talk a little bit about what we call the geometric mean. The geometric mean. So looking at this one, so we were looking at these two triangles. X goes to Z as Z goes to Y,
Right.
right? little bit of algebra, multiply both sides by y, multiply both sides by z, or in other words, looking at our theorem from before, that times that equal to that times that. So this gives me that
X over Y is.
x times y is equal to z squared. Or z is equal to the square root of x times y. So you're used to calculating an average. If I were to ask you, let me think of numbers that'll come out nice. 3 and 12. What's the average of 3 and 12? Huh?
Oh, average?
Yeah.
Average of 3 and 12.
Yeah.
It's 9? No, it's not
No,
9. It's
it's
like 7.
3 plus 12. It's like.
Maybe 7.
No,
It's like 7.5.
Like
It's exactly 7.5.
7.
Alright, how do you calculate that? All you did was 3 plus 12, and then you
Divide
divided by 2. So it gave you 15 over 2, which is the same thing as 7.5. Okay, we call that the arithmetic mean.
The what?
In the arithmetic mean,
Arithmetic.
as in arithmetic.
Mm-hmm.
Arithmetic mean. And 7.5 is somehow the middle of these two numbers.
Right.
Now, if I would have constructed this so that x was equal to 3 and y was equal to 6, what would z be equal to? Or sorry, if x was equal to 3 and y was equal to 12, then z would be equal to the square root of 3 times 12, which is equal to, what's 3 times 12?
36.
36. What's the square root of 36?
I'm not good spurs. It's
What times what is 36?
6 times 6.
6.
6. So the square root of 36 is just 6. So 6 is the geometric mean of those two numbers. So sometimes it's useful to calculate an arithmetic mean. Sometimes it's useful to calculate what we call a geometric mean. And what's cool is these right triangles encode that geometric mean, which is why it initially got that name, geometric mean. And so there's another sense in which 6 is in fact the middle of these two numbers, the average of these two numbers. So that's what's meant by the geometric mean. Now most people when they say average, they mean arithmetic mean, but
That's interesting. So is it the same? Is another way to get the geometric mean to multiply the small one by 2 and divide the big one by 2?
no.
It's equivalent on this one. Just wonder if that's just like this. It's just
It might have come out nice
That's
on that
just
one
a,
because I had to pick two numbers that weren't the square root numbers, but when you multiply them, the square root's easy to take. So 7 squared would be 49. That's harder. 8 squared is 64, so I could have done something like 16 and 4. So what's the average of 16 and 4?
It's the same thing.
8.
You divide the small.
In that case, the
Yeah.
arithmetic one
The arithmetic is 10.
is 10, but the geometric is 8.
Right, and that's what I'm saying. It's the big ones, the big number, the larger numbers divided by 2, and the smaller numbers multiplied by 2.
What?
And then it's
Okay.
Isn't that cool? Same.
So we picked two where that happened to be the case. Let's
Let's pick another one, see if it's real. Well, I'm saying if it's a real, if it's a, what do you call those numbers?
so here's let's really quick put this to rest. So what's the average of 64 and 1?
Average of 64 and 1 is
32.5.
2.2. Yeah.
Now what's their geometric mean? It's still just 8. 64 and 1 have the same geometric mean that 16 and 4 had, or that 8 and 8 had, or that 32 and 2 had. These were all sets of numbers with the same geometric mean.
Okay.
But if I calculate the arithmetic mean of all those, I get very different answers. Okay, so it was just an accident that the numbers I was choosing, that pattern kept showing up more. Okay, so there's that picture. Now I want to use that picture to prove the Pythagorean theorem. So now we're going to do our proof of the Pythagorean theorem. And it piggybacks on the same picture. What is the Pythagorean theorem? What am I trying to prove? I'm trying to prove that the square of this side is equal to the square of this side plus the square of this side. And I've already shown you a nice geometric, very pictorial proof of this fact. So now we're going to use similar triangles to prove this fact. Okay. And let's see how I want to do this. So looking at relationships between this triangle and the big one,
Yeah.
I know that x goes to a, small goes to hypotenuse, as
A goes to B.
a goes to c,
C, sorry.
as small goes to hypotenuse. Similarly, looking at this triangle, I know medium goes to hypotenuse, y goes to b, where
Same
medium
way
goes to
that B
hypotenuse,
goes to C.
as b goes to c, medium goes to hypotenuse.
And the same way that Z goes to A.
Well, we just need these two relationships.
Okay.
So now, taking this one right here,
Right.
solving for x, just multiply both sides by a, I get x is equal to a squared over c. Solving for y over here, I get y is equal to b squared over c. You with me?
Yeah.
Now finally, c, this whole length, is equal to x plus y.
Right.
So c is equal to x plus y, which is equal to x plus y.
Right.
So c is equal to a squared over c plus b squared over c. Multiply both sides by c. So I get c squared is equal to, c's cancel out, leaving us with a squared, plus c's cancel out, leaving us with b squared. And so a squared plus b squared equals c squared, the Pythagorean theorem.
That is awesome. That really was cool.
And so there's the proof using similar triangles. Not near as much work as drawing out the pretty picture I showed last time, making the argument with areas.
Right, yeah, that one was pretty complicated.
So let's see what he does next. Prove the converse of the Pythagorean theorem. Proving the converse of the Pythagorean theorem, this almost falls for free. So the Pythagorean theorem is, if you have a right triangle, then a squared plus b squared equals c squared. What's the converse? The converse is, if you have a triangle such that a squared plus b squared equals c squared,
It's a
then
right
you have a right triangle.
So the Pythagorean theorem only works for right triangles?
Yes, it works. So we know that it works for right triangles, and now we're going to show if it works, then you have a right triangle. So we're going to assume that we have some triangle. Maybe not right, we don't know. I've got some triangle here with side length A, B, and C. The question is it a right triangle? How am I going to prove it's a right triangle? I'm going to come over here. I'm going to construct this right angle. And I'm going to make this bottom length B. And I'm going to make this side length A.
Okay.
You with me?
You're going to prove that the angle between those two is
So
C
now,
and C.
connect those points. I know that this side length then has to be C.
Okay.
Right?
Yeah.
So, this triangle is congruent to this triangle by side, side, side. So that's a right angle.
Right. Wait a second, how did you get there?
Yeah.
Alright, let's restart.
Wait.
So I've got this triangle.
Right.
I've got this triangle, and all I know about this triangle is that a squared plus b squared equals c squared. That's all I know.
Right.
Okay.
So now make a right angle,
I make a right
A
angle over
and
here
B.
with a and b.
and then you draw a line.
Now I know that the length of this side has to be the square root of a squared plus b squared.
Just see.
It has to be from the Pythagorean theorem. This is a right triangle.
Right.
And if,
So
But-
now you're showing the side they're the same triangle.
But that is what c is.
so you're replacing those numbers as lengths technically, right?
Yeah, these were meant to be
These are
lengths
our numbers, yeah.
of that.
Thus, okay, because then you have side.
Right. So you say, is this a right triangle? Well, construct a triangle that is a right triangle that has two of the same side lengths.
Same
The
length.
third side length has to be the same.
Right.
And so they're congruent.
Right.
So it's pretty trivial to
Therefore,
show
it
the
is a
converse.
right
Right?
triangle.
Therefore, this is a right angle since they're congruent by side, side, side.
Right.
Okay, and then finally our last one, another full one.
There's one more after this. There's 914.
Oh, I'm not gonna do 914, or yeah, 914. That's just the one that we already talked a little bit about. If two circles are close enough, they intersect at 2 points. Just calculate the 2 points of intersection using the Pythagorean theorem. I don't think it gives you much. So we'll go to the last one. The last one, pretty cool one. Probably fit it right here. The last one says pick any semicircle you want. So we're going to start out with half a circle.
That's pretty simple.
We're going to make one point of the diameter a vertex of a triangle, another point a vertex of a triangle. Now we pick our third point to be anywhere along this circle. Doesn't matter where.
Okay.
I'm going to arbitrarily pick it to be right here. So it creates a triangle.
Right. That's a right triangle.
It turns out that that's always going to be a right triangle. So
That's
any
so
triangle, we call this inscribed in a semicircle. Any triangle inscribed in a semicircle is a right triangle.
Wow.
So this is a circle, I may call this point O. The distance from here to here is the radius of our circle, whatever that is. The distance from here to here is also the radius of our circle, whatever that is, right? I'm trying to argue that this angle up here is a right angle. That's my goal.
Right.
Okay, what I'm going to do is I'm going to drop an altitude down. So this is going to be right angle, this is going to be a right angle. And whatever point it hits here,
Now we're going to prove the opposite of what we were proving last time. Is that what you're saying?
we are going to be arguing to the fact that this is a right triangle.
Right, but I'm saying the one up top over there, we're going to prove the opposite of that. We're just going to like twist it backwards, kind of.
Well, honestly, I'm not sure where I'm going with this yet. So, just thinking it through so far.
Right.
So, wherever it drops that altitude, that's going to divide this up into side lengths. Call it x, y, and then we'll call it height z.
And together they are x and y equal r. That's just,
But yes, you're right that it's like reversing this picture that we have here. I see what you meant by that.
yeah.
Yes. Okay. So, let me think. I'm trying to argue, I know that this is a right triangle. I'm trying to argue that this is a right triangle, so I need to, if I argue that it's similar, we get it. So I need to argue for some proportionality. What proportionality do we want?
That is tricky.
So I could argue that x over z is equal to is that the one I want? Or do I want to argue with this triangle?
I think you want to do both, don't you?
So let's see, small over medium, I want to argue is equal to small over medium is equal to z over y plus r.
Right.
Okay, so if I can argue, let's skip ahead into thinking to make sure I got the right idea. So I think that that will be the crux of my proof. Because if I can argue that that triangle is similar to that triangle, what that would make is this angle
Is congruent.
would be the same as this angle,
Right.
and then this angle would be the same as this angle. And so, since that angle plus that angle are a right angle, that angle plus that angle are a right angle. And so it's a right angle.
Oh,
So what's the angle sum of a triangle?
180 degrees.
Subtract 90 degrees.
Now it's 90.
So
Right.
that plus that is 90, so that plus that has to be 90.
There you go. Right, okay.
That's logical. So if we can establish this relationship, we're good.
Right.
So it comes down to arguing that relationship. So here's what I'm trying to argue. Let me solve for some variables here. So we can do some, I guess we'll just do here. So I need to figure out what x equals. Let's solve for x. X is equal to, looking at this triangle. I don't know that side length.
What side length?
I guess I do. So this side length over here, what is the length of this side? That is the square root of x squared plus
Z squared.
z squared. but then that just rewrites it in terms of x and doesn't get rid of my variable.
I think what we want to say is label is a, and then a over x is the same thing as.
Ooh, I know that x is r minus y. That's what I'm going to use for my x.
Right.
I'm just trying to get rid of two variables
Right.
so that I can solve this thing. So I know x is equal to r minus y. Okay, so I got that. Let's see what my z is using this triangle.
Z is.
So I'll write everything in terms of r's and y's. So I got x in terms of r and y. Let me get z in terms of r and y, and I think we're good. So z is equal to, we know that, do a scratch work over here. I know that z squared plus y squared is equal to r squared, right?
Yes.
From this right triangle.
Right. So now you know that r squared minus y squared is z squared.
Perfect, is equal to r squared minus y squared. Take the square root. So I know z is equal to the square root of r squared minus y squared. Perfect, so there's my z. So z is equal to the square root
R square root, which is
of
r
r
over,
squared minus y squared.
which is r over. Is the square root of r2 over minus y2 r minus y?
No.
It's not.
Let's do quick sanity check. Thinking of a good difference of squares. 3, 4, and 5. 3, 4, and 5. Okay. So the square root of 5 squared minus 4 squared. And we're going to look at 5 minus 4. 5 minus 4 is 1. Okay. So now let's see what we get with this. 5 squared is
25.
25 minus 4 squared is
16.
16. 25 minus 16 is 9. So this is square root of 9, which is equal to 3. So 3 is not the same thing as 1.
Very good. Right.
Okay.
Thank you.
So anyways, so let's figure out what x over z equals now. So x over z is equal to r minus
R
y.
minus y over the square root of r2 minus y is 2 squared.
r2 minus y2.
Yeah.
Now, here's what you were confusing. I'm going to put this under a radical by squaring it. So this is true. So this is the square root of r minus y, the whole thing squared, all over the square root of.
Oh, right, and then that cancels it out.
But I'm going to factor this one. R
Square
squared
root
minus
of the
y
square
squared is r minus y times r plus y.
It's r squared, r.
No, how do you just. Oh, okay, I see it.
R times r squared. Negative y times r is negative ry.
Now you can cancel
R
out the
times y,
squares.
positive ry. Negative y and positive y gives us negative y squared.
Now
See
you
the
can
algebra?
cross out the square roots.
Okay, so now r minus y will cancel out with one of these r minus y's. Probably shouldn't have said that yet. Having the denominator in a square root and the numerator in a square root, let me say it up here. The square root of a over the square root of b is just equal to the square root of a over b. Not, you can't cancel out the square roots. You can put the whole thing under a radical. So I can put the whole thing under the radical. And now it probably makes more sense that I cancel out that with one of those, leaving r minus y in the numerator. So this is equal to the square root of
R minus
y over r plus y. Okay, so now let's go figure out what this equals, and we better get the same thing or we messed up. So now z over y plus r is equal to, what's z? Square root of r squared minus y squared, all over. I'm going to square this and put under a radical. Square root of y plus r, all squared. With me?
Yeah.
This is equal to, since the numerator and denominator are both under the radical, just gonna put the whole thing under a radical.
Right.
And now r minus y, that's the same thing as r plus y times r minus y. All over r plus y squared. Maybe just write it out to make sure we see exactly how we're canceling. R plus y times r plus y squared, same thing. We have an r plus y on top and bottom, those cancel out.
Right.
We're left with the square root
Of r minus y over.
r minus y over
Over
r plus y. And what do we know? We get it. So that and that are equal to each other. Therefore, this triangle is similar to that triangle. Therefore, the big triangle is a right triangle. Remember the logic we were after? So showing that these two sides are proportional.
Right, showing those two equal, then we got it. Which we did.
We have one side, we already knew that So we're looking at the two small right triangles, not the big one.
Right.
So the right-hand one and the left-hand one.
Right.
We already knew that they had an angle in common. We just proved that they had a proportionality in common. Therefore, these two triangles are similar. Now, notice that the angle sum of any triangle is 180 degrees. Get rid of the right angle.
Right, now,
That angle plus that angle has to be 90 degrees.
so
But that angle is the same as this angle, since the two triangles are similar.
Right, therefore,
So this angle plus this angle is 90 degrees, so this whole thing is 90
90
degrees.
degrees.
So it's a rectangle.
Okay.
And that's the proof. Cool. That was a bunch of fun ones today.
Yeah, it was.
Very pictorial. And I think that was the last one, right?
Yeah. Right, so we skip 9:14.
Yeah, that other one. That's interesting. Okay, so next week we get to start talking about areas. But yeah, take the time on the homework. I'm guessing that this chapter 9 homework is going to be the hardest in the book.
It's long.
Using these relationships between triangles. I don't know that the chapter is very long.
It's not long.
It was just a lot of proofs. I think we only covered like 20 pages.
Well, it just has each. There's not many proofs either in the actual homework. There's really not.
Yeah, so chapter ends on 176, start on 154, 22 pages.
Yeah.
So it just happened to have a lot of proofs
It
in
had
that.
quite a few proofs
part of
in
the book.
it, but the homework really doesn't have many proofs.
Yeah, so hopefully not too bad for you. But yeah, we'll take 2 weeks to do the homework on this one. Any questions on that?
Not yet.
Not yet.
We will only start the homework.
Oh, I figured out that other problem. The one with the sides. I guess we don't need to record this. So anything else we want recorded before I turn it off?
I think so.
All right, so we'll end that there.